Thank you very much for the warm introduction. I would like to use the next approximately 10 minutes, I hope, to put a master thesis into the spotlight that we had at our institute.
Sorry, we have 15 minutes. Like you have 15 minutes.
15?
Yeah, we have full hours, so yeah.
All right, let's see what I can do. Anyway, I want to put a master thesis into the spotlight, which we had at our institute, dealing with the assessment of climate effects resulting from the airspace closures that we had following the Ukrainian crisis. I know that you are all aware of the effect that the Russian invasion of Ukraine had into basically every aspect of life. But of course, it also significantly influenced aviation due to the general closure of the Ukrainian airspace on the one hand side, and a ban of overflights for the Russian airspace applicable especially to Western airlines. We know that this required detours, which of course influence travel times, but also fuel consumption, emission quantities of CO2, but also nitrogen oxides, water vapor, aerosols, and so on, but also, of course, the climate impact. And the special thing about the climate impact of aviation is that it is not significantly only determined by CO2 emissions, but also by approximately 2/3 of the total effects of non-CO2 emissions. And what's especially interesting about those effects is that it varies significantly with the emission altitude, but also the emission location in a lateral dimension, as well as the time of emissions. If you, for example, think about the climate effects of contrail, which differ significantly between day and nighttime contrails. There has been quite some research in this topic, focusing on the aspects of flight cancellation due to that invasion, the increase in flight distance and fuel consumption, as well as also the increase in CO2 emissions. But there has not yet been an assessment of the climate effect been performed. And this is exactly what was the research objective of this master thesis and also the paper that we're currently preparing, where the goal is to assess the climate impact from those airspace closures resulting from the Russian invasion of Ukraine and the resulting airspace closures. If we look at the method that we applied, it's basically a 3-step assessment workflow, and it starts with the database of OpenSky, where we gathered the point profile data and performed a scenario preparation leading to actually 2 scenarios, one scenario prior to the invasion and one scenario after the invasion, representing the war situation, so to say. Those traffic data is then fed into our trajectory calculation module, which applies realistic weather data, as it can, for example, be derived from ECMWF, and we also use flight performance data. In this study, we now focused on BADA4 flight performance data. I know it's not open source, but we've extended the tools or the capabilities of our tool. And it's now also able to also incorporate Junzi's OpenAP flight performance modeling, as well as the open source Paul Schumann model. The trajectory calculation then gives us the 4-dimensional flight performance data, such as the different forces, thrust, drag, but also fuel consumption and meteorological data along those trajectories. We use this then to feed this into the emissions calculation, which we perform with a tool which has been established at DLR named GridLab, and it takes the ICAO engine emissions data in a fuel flow correlation method and then calculates the 4-dimensional emission flows along the trajectories. This has been integrated in a new tool that we call integrated TCM, and this is then directly coupled with the climate impact assessment, where we can, for instance, use simple regression formulas for the climate impact assessment, but also more sophisticated models such as algorithmic climate change functions or the global climate chemistry response model AIRCLIM. And this then gives us the climate metric of average temperature response over 100 years in this example, but we can also look at different climate metrics such as energy forcing, radiative forcing, global warming potential, and so on. So all in all, it's a, as I said, 3-step modeling chain to assess those flight trajectories. And we can assess, of course, the detour, changes in flight time, fuel consumptions, emission quantities. But the major benefit of this chain is then that we can also assess the climate impact. Regarding the data that we applied, I already mentioned that everything is based on the openly available open source ADS-B data from OpenSky. And the data was filtered for flights that were crossing the relevant airspace, so Russian or Ukrainian airspace, and in the pre-invasion situation. We used Xavier's OpenSky traffic library for the preparation of the data. And in the master thesis, we focused on 2 case study days, but we are, of course, planning to extend also the temporal scope of that study. So we have 2 days, January 28th and March 25th of 2022, which are both approximately 4 weeks before or 4 weeks after the start of the war. And it's the same weekday, so that we can at least exclude some some variations of the air traffic during the week. Nevertheless, quite some manual processing of the data was required to actually match the flights pre and post invasions, so that we had a comparable data set to perform our analysis on. Finally, we ended up with 252 missions that we compared for the 2 scenarios done. There are some descriptive statistics here on the right-hand side, but just one point I would like to draw your attention to is the different airlines that we consider. These are the top 10 airlines now. And you can see the bars that are indicated in green. Those airlines are still allowed to cross the Russian airspace, while the European airlines, for instance, had to avoid this region. Coming to the results, I brought one very prominent example, I'd say, where we see that especially the operations from Europe to Asia is strongly affected by the restriction to avoid the Russian airspace. This is a mission from Helsinki to Singapore, and we see that flight distance increased by approximately 10%, fuel consumption by approximately 9%, and the climate impact in terms of average temperature response over 100 years by 8.3% for this single mission example. Of course, this also has significant economic consequences for the operating airlines, and the very long detours might also require the change of the aircraft type for some operations. And what we also found in the analysis is that some routes are not operable anymore because they are just too long, and an intermediate stop has to be performed, for instance, in Ireland or somewhere. Another example, which I find quite interesting, is the comparison of the same route covered by 2 different operators. So we have a mission here from, I think, Chicago to New Delhi. And we have it, if it is covered by United Airlines, avoiding the Russian airspace in the post-invasion scenario, we also see a significant increase in flight distance, fuel consumption, and also an increase in the climate impact. But if we look at the same mission, which is if it's covered by Air India, we see that all those KPIs remain almost unchanged. We see even a slight decrease in the considered KPIs, such as flight distance, fuel consumptions, and the climate impact as well. If we now look into the total sample of flights that we considered, I think it gets quite obvious that the Ukrainian airspace is obviously totally avoided in the post-invasion scenario, but we see that quite some flight missions still cross the Russian airspace in this example. All in all, we find an increase in flight distance of approximately 2% for a sample, flight duration of 2.3%, increase in fuel consumption and CO2 emissions in approximately the same order of magnitude, and also an increase in nitrogen oxide emissions and soot emissions around 3%. If we now go into the details of the climate impact assessment, we found something which was quite surprising. Although the emissions increase, the climate impact does not increase. And this is due to the changes in the position of the emission locations. So we see that the climate impact from CO2 emissions, of course, increases proportionate to the increase in CO2 emissions. But the climate impact from the other emission species that we considered could be reduced to changes in both emission altitude and emission latitude. And this then led us to the result that the overall climate impact from our sample could be reduced by, or was reduced by approximately 1.4%, which is quite surprising. We didn't expect that outcome from this study. If we then also go a bit deeper into the details, and if we split the sample into the European and US airlines on the one hand side, and the, I call it other airlines on the other hand, we see that there are quite some differences, of course, and we can highlight the differences or the advantages that the airlines still had from crossing the Russian airspace regarding fuel burn and also climate impact. So for the European and US airlines, we saw distance and fuel burn increased by approximately 4%, climate impact decreased by 2.6%, and 0.7% for the other airlines, and a lower decrease in climate impact for those airlines. To sum it up, what did we find out? So obviously, of course, the airspace closures and bans of overflights resulting from the Russian invasion of Ukraine have significantly influenced international air traffic. We found increases in flight distance and fuel consumption of approximately 2% for our sample of approximately 250 flights. However, we found a decrease in the climate impact from the non-CO2 effects, which also turned around or overcompensated the impact from the increase in CO2 effects. And what we also found were some high impact missions where we had up to 28% of required detour for long range mission, which also required a change in the fleet assignment in some cases. The study also showed a competitive advantage for those airlines that still cross the Russian airspace in contrast to those airlines that do not cross it anymore. And if we look out to further research that we are planning to do, I think it makes, of course, sense to extend the flight sample and the temporal scope of the study, because we have now only looked at a comparatively small flight sample as well as the only 2 considered days. We would also like to investigate the impact on a global scale, so also in relation to those missions that have not been affected. We would like to extend the analysis from the climatological climate assessment to also considering the actual weather situations, as it can, for instance, be done with algorithmic climate change functions or the open source model PyContrails. And it would, of course, also be interesting to look into operating cost changes and necessary network changes for airlines, as well as changes in revenues for the different airline types. And that's it from my side. I'm now more than happy to take your questions.
So we have several questions. Let's start with...
You have presented something. Thank you very much for the presentation. Really interesting. I go to the plot quickly because we have not too much time. We have presented something that is really surprising, and you say that is surprising. If all the things we are doing is to reduce the routes and to reduce the fuel consumption, and having longer routes means less, and this is due not for economical reasons, but mainly for climate change. And we see that enlarging the routes reduce the climate change impact. I believe, I don't know if you have a long list of things to do, but I see the first one on the list. Why? What is happening there? Because probably all the rest of the scheme for the future of aviation, looking for reducing things, could be completely changed. It is possible, but apart from economical reasons, as you have said, it is better to fly different routes because of dispersion of the routes or whatever.
Yeah.
So really interesting.
Yeah, I totally agree. I think this is also what we'll, if we go away from this study now and more look into climate mitigation potentials, I think there are quite some studies around demonstrating that avoiding especially climate sensitive regions is quite promising to reduce the non-CO2 effects. However, we also have to say that we are quite certain about the CO2 effects, but the non-CO2 effects still remain quite uncertain in their quantification. So it's always a trade-off between avoiding like the certain CO2 effects or avoiding the non-CO2 effects with the higher climate mitigation potentials, but where we will still have large uncertainties. But yeah.
Thank you, Sarah. Thank you very much for the very nice, insightful presentation. Yeah, I just also want to continue on this line of thinking, because I just want to know that this climate impact and also CO2 impact, the reduction is not due to the less number of flights, right?
No, it's the flight samples are exactly the same. So we are 252 in the pre-invasion scenario and 252 in the post-invasion scenario.
Yeah.
So the flight numbers are equal, and it's the same origin-destination pairs that are connected.
Yeah. So could it also be possible this model are simply not accurate, because this is very counterintuitive? Because if I think about it, because the climate model is part, it also considers both CO2 and non-CO2.
Yeah, but
right?
Yeah, absolutely right. We considered the AIRCLIM model, which considers both CO2 and non-CO2 effects. And if we look at the metric that we looked at of ATR 100, I think we can say that CO2 effects account for approximately 1/3 of the total effect, and we have 2/3 of the non-CO2 effects. And those non-CO2 effects vary significantly if I lower the latitude and also if I change the altitude. And this is why in this study, those non-CO2 effects overcompensate the CO2 effect. So we see a rise in climate effect from CO2, but they are overcompensated by the non-CO2 effects. And this is since the flights are performed at lower latitudes, it's less likely that contrails are performed in those regions. And if we select ATR 100 as a metric in this study, it's overcompensated. Yeah. But I also showed the plots, but of course I didn't have that much time to go into all the details. The variations are also quite large. So if we look at the median values, the differences are not that big. The mean values show a significant difference. Yeah.
There's also a group, if you go back just a few slides. So you have the US and a European flight, and then you have I think those probably Chinese flights, like the other airlines. So I was actually traveled to China like last week, and I was able to fly over the Russian airspace. Yeah. And here you see interesting thing is that there is slightly increase in the fuel burn more or less, but you have a much less reduced ATR impact in terms of climate, right? If you look at the final column, minus 0.04, sorry, the second row of the last column. It seems to me that by flying over the Ukraine region, increase the climate impact.
I mean, the study was organized the other way around, but we showed that if you avoid this region, I mean, the goal is not to avoid this region for climate reasons, but the lower latitudes, because you typically fly a more southern route, the climate impact, especially from the contrails, is then reduced.
It's just for me, it's a bit counterintuitive, and it raises a bit more question on the models themselves, right? The extent of climate impact from the contrail, and is it really that significant compared to the CO2? Not your model, but the model underlying this evaluation.
Yeah, so quick comment, and then we can take the...
Sure.
Yeah.
Thank you, Junsi. Just to comment on your question regarding the models. I mean, I know that we at DLR are very familiarized with this, and I think in the context of this conference, when we look at fuel flow, it's typically in terms of efficiency on network level. For us, it's something that has been studied in literature. The studies exist specifically from DLR atmospheric physics. And there's, I think in this case, a certain tendency to fly on lower latitudes, which generally has shown these effects of lower contrail-induced cirrus. And that's where the effects come from. Of course, they are bound to the uncertainties that Sarah has already mentioned. But in general terms, this is something confirmed by several models, including, I think, also EMAC from TU Delft, right?
I've never seen this in reality like this analysis that is such as such a contrast.
Yeah, maybe just to add on this real quick, and then I'll just leave this stage to the next speaker. But there are quite some studies where we look into climate optimized flight planning. And in those cases, we typically trade an additional fuel burn, additional CO2 emissions and climate impact for a reduction in non-CO2 effects. And that's, I mean, this is a different context, but it's the same results that we see. Yeah.